Welcome back. This video is brought to you by Forge College as an educational resource to sharpen your Web3 development skills. Today, we are diving into exploring pattern libraries and selection, which sits right at the core of our Designing Smart Wallet Patterns course. In the previous lesson, applying network selection to use cases, we figured out where our application lives on the blockchain. Now, we must tackle the next logistical hurdle, deciding exactly how your users will access it. Often, developers guess which wallet pattern to use based on whatever is currently trending on developer forums. That approach results in bloated applications that require a manual to operate, or frustrated users who abandon your onboarding flow halfway through. Guessing your wallet architecture is a massive waste of engineering hours. To fix this, we need a systematic, defensible way to select the right pattern for the right user. Every Web3 builder eventually hits the same dilemma. You have a philosophical tug-of-war between demanding maximum cryptographic security and wanting a seamless, frictionless user onboarding experience. Debating security versus user experience in abstract terms is useless when you actually sit down to write Solidity code. You need hard metrics, not philosophy. This graph maps that relationship. Along the bottom is the friction scale. 0 means instant setup. 10 means complex coordination and hardware keys. The central rule is not maximizing security, but matching controls to an acceptable friction level, dictated by your threat model. By defining exact friction limits up front, you immediately eliminate dozens of inappropriate wallet patterns before your team writes a single line of code. To make this process repeatable, we use a pattern library. Think of it as a repository of vetted, battle-tested smart wallet designs that we can pull from. Of course, a library is entirely useless if you can't search it. We need to reduce these complex architectural patterns into a strict metadata model. This is how metadata is structured. It tracks the pattern's name and explicit security features via an enum. Next, we attach a friction score, mapping back to our graph. Finally, implementation notes track hidden engineering costs, like helper contracts, Oracle dependencies, and gas overhead. This struct serves as a concrete contract between the product team and the engineering team. It ensures everyone agrees on the exact technical cost of a user experience decision. Let's put this metadata to work against a real-world scenario. Imagine you are tasked with building a consumer mobile wallet. The constraints here are ruthless. Your users have zero patience, require very low cognitive load, and need to execute fast daily transactions without signing multiple prompts. This matrix shows how we evaluate candidate patterns. If we test the simple recovery plus device key pattern against these constraints, we see a low friction score of 3 out of 10. It fits the consumer profile perfectly. The trade-off is that this pattern completely lacks auditor controls or multi-party approvals. If we test the on-chain multisig pattern in that exact same consumer scenario, the friction score of 7 out of 10 would absolutely destroy the app's onboarding metrics. For consumer apps, your primary threat model is simply surviving the first 3 minutes of user attention. That makes low-friction patterns the only viable choice, despite their lower absolute security. Now, let's pivot. Your next task is building an enterprise custodial wallet to manage institutional funds. The constraints completely flip. You now have strict separation of duties, mandatory compliance audits, and a pressing need to protect against insider threats. If we reevaluate the threshold signatures 2 of 3 pattern here, we accept that it introduces more friction, but it perfectly solves the enterprise single key risk problem. The implementation reality is that this choice requires building off-chain verifiers and coordinating signing windows, which means significantly higher development costs. Notice that the pattern itself didn't change, your context did. Enterprise users gladly trade setup friction for institutional safety, proving that friction is relative to the stakes. To replicate this selection framework in your own projects, we use a repeatable 5-step workflow checklist. It takes your team from browsing an abstract library to making a final decision in about 30 minutes. Steps 1 and 2. Define your specific threat model. Then aggressively filter out any library patterns that lack the mandatory security features to defend against that exact threat. Step 3. Score your remaining patterns based on their numeric friction and their implementation cost. Step 4. Run scenario tests. Focus specifically on exceptional flows, like account recovery, because that is where hidden user friction usually lives. Step 5. Document your required primitives like necessary oracles or helper contracts and write down the formal justification for your final pick. Documenting that justification prevents feature churn later. When requirements inevitably change, you have a written record of exactly why a specific architecture was chosen in the first place. Ultimately, you cannot choose a wallet pattern until you know exactly who you are building for and what they are willing to tolerate. This flowchart breaks down the decision tree, starting with what is your primary constraint. If speed is paramount, default to simple recovery and device keys to combat bounce rates. If compliance and scale are paramount, default to threshold signatures to satisfy your auditors. The best pattern is simply the one whose trade-offs align perfectly with your product's survival metrics. Selecting the pattern is only half the battle. The next challenge is designing the UI to hide the friction we just calculated. In our next lesson, Principles of Smart Wallet Interfaces, we will build the user-facing flows to accommodate these specific patterns. Before you start that video, take one pattern you like and run it through the 5-step checklist we covered today. This guide was created by Forge College. To learn more about applied Solidity development and to continue building your Web3 education, visit us at forge.college. See you in the next lesson.